one of the tools we have is to do magnetization loops. So we apply a field, measure the magnetic response of the sample, then go back. We see that we have an irreversible magnetization, and from the shape of that irreversible magnetization loop, we can get at different things. So first one is that the difference between, so this we start with this, go here, and then we reverse the field, jump here, and then go back. So we will see an irreversible magnetization for this field region. So at the given applied field, we will see a difference in the magnetic response for field up and field down. And this one, delta M, this is proportional to the critical current density. And this comes from the well-known critical current model, in which it is assumed that the critical current in a material is constant all over the place, and when the sample is fully penetrated, it happens a lot of things. So actually, we have in this model that critical current density is proportional to the difference in this magnetization. Now, depending on the geometry of your sample, you can have different ways to take JC from this value, this is the experimental value. And in the case of my work, in which it was on thin films, it is shown that JC can be described very well by this formula, in which M is half of this irreversible magnetization, D is the thickness of the film, and A and B are the rectangle dimensions of a film, which is assumed to be a rectangle. So it's easy to get from here to the current density, apart from very small magnetic fields, because there are some different things happens, and these measurements underestimate the actual value of JC at very low fields. In my project, we were not using very low fields. We wanted to improve the current density for high fields. Okay, some other things we can take from these magnetization measurements. We can, well, the pinning force is the vector product between applied field and JC. So the pinning force is the one which opposes the movement of vortices, and it is given by the product between field and current, same like the Lorentz force. Now, from the measurements we have, we need to find out what type of pinning centers can we have. And one of the first very nice models is the Hughes model. Well, it was quite old. It dealt with classic superconductors. But he did a quite nice analysis of the shape of this ratio between the pinning force and the maximum pinning force as function of the reduced field. Now, in Hughes model, he uses H equals B divided by B C2. In high density superconductors, the actual value should be B divided by irreversibility field. So if we look at the ratio, the normalized pinning force, as function of applied field, we will see that they can be described by this type of equations, in which we have the reduced field at the power P, 1 minus reduced field at the power Q. And these P and Q, the exponents, they depend on the types of pinning centers. Now, the pinning centers, they are classified by two things. First one, by the number of dimensions that are large compared with the interflux line spacing. And second, by the type of the core, delta K pinning and normal pinning. So what is normal pinning? Normal pinning comes from small regions in which we have a local variance of critical temperature. So in a certain sense, we have a region in which for certain temperatures that becomes like more normal than the others when you apply a field. Delta K pinning, it's the type of pinning which is provided by regions in which we have slight variation of the Ginzburg coefficient, K equal lambda over psi, and it refers to impurities which are doing some sort of scattering. Now, usually there are more than one type of pinning centers. So an actual curve, if you want to plot the reduced pinning force as a function of applied field, you will have a combination of such expressions. So what we have, a small part of one type of pinning center plus a small part of another type of pinning center plus and so on. Okay, let me make it more clear to you now. So,
Adrian, you can have a break anytime you think sweet out.
When they want to.
15 minutes should be okay, because we...
It's too much.
The break time. You can decide about the break time. So when you say...
We can start from here, so no problem.
We can continue from after 15 minutes.
Yeah, sure.
If
it was too much...
On the first day, maybe they will
If
get
it was
off.
too much, okay.
Okay.
Yeah.